As artificial intelligence, AI, permeates every aspect of our lives, ethical questions surrounding its development and application are becoming central to public discourse. From algorithmic bias to personal data protection, the spectrum of dilemmas is expanding, demanding comprehensive analysis and the development of responsible approaches to AI advancement. But before we continue, let's look at the vastness of space to understand the scale of the challenges facing science. Before you is the spiral galaxy NGC 2008, captured by the Hubble Space Telescope. In contrast, the M87 galaxy exhibits an elliptical shape. While determining the shape and structure of distant galaxies seems relatively straightforward, attempting to define the structure of our own galaxy from within presents a true challenge. Imagine trying to take a galactic selfie while immersed in its depths. Nevertheless, images exist that purport to show our galaxy, depicting its disk, spiral arms, and even the approximate location of our solar system among the myriad stars of the Milky Way. It's crucial to understand that these images are not definitive projections of our galaxy. Its structure, shape, and the arrangement and number of its spiral arms are constantly being refined as new data on the velocities and coordinates of stars, star clusters, and gas and dust clouds become available. Despite these challenges, astronomers have made significant progress in mapping the Milky Way. Today, we know that our galaxy is a barred spiral galaxy. But how did scientists acquire this knowledge? This is precisely what we will discuss next. When describing Earth's position within the galaxy, astronomers often use the analogy of a dense forest. Imagine yourself deep inside this forest, surrounded by countless tall trees, and you are tethered to one of them, unable to move. Furthermore, the forest is shrouded in a thick fog, obscuring its distant reaches. Under such conditions, the task of determining your location and creating a map of the forest becomes incredibly difficult. We will discuss later why this analogy isn't perfect, but for now, let's start with the obvious. The first step to understanding our galaxy's shape is visual observation. The bright band stretching across the sky, known as the Milky Way, is visible to the naked eye, especially in areas with minimal light pollution. As early as Galileo's time, people realized that this band represented a dense concentration of stars. Thus, it can be concluded that our galaxy most likely has a flattened disk shape, rather than an elliptical or irregular one. Otherwise, the stars would not form a band but would be distributed across the entire sky. Additionally, within the starry band, a brighter, larger bulge-like formation can be seen extending beyond the disk. This structure resembles a bulge, the elliptical component of spiral galaxies. However, even understanding that these observations suggest a spiral structure, one cannot be entirely certain, as we only see a portion of the galaxy's disk. To gain a complete understanding of the Milky Way, it's necessary to combine numerous images taken from different vantage points. The 2-mass all-sky astronomical survey demonstrates what our galaxy looks like. This infrared image merges data collected by 2 telescopes located in different hemispheres of Earth. In this 2-dimensional representation of the celestial sphere, the Milky Way appears as a disk galaxy viewed edge-on. But how did scientists manage to establish that our galaxy has a spiral structure, and even create a map indicating our location? The key to constructing any map lies in determining the location of objects and measuring their distance. However, for objects like stars or gas and dust clouds, this task is incredibly complex, especially on the scale of an entire galaxy. In the past, particularly in the 19th century, astronomers could not explain the nature of vast cosmic regions along the Milky Way that appeared devoid of stars. These areas, known as coal sacks, looked like dark holes against the bright starry sky. Today, we know that coal sacks are simply clouds of gas and dust blocking starlight. At that time, research was conducted exclusively in the optical range, which, unlike radio waves, cannot penetrate the numerous gas and dust clouds within the galaxy. It was only with the advent of radio astronomy that scientists gained the ability to peer into the distant corners of our galaxy, hidden from optical observations. But what did they see there? You will find the answer to that question next. Radio waves offer a unique opportunity to explore space, allowing us, for instance, to pinpoint the location of cold and warm hydrogen. Surprisingly, even the simplest element in the universe, hydrogen, can emit energy in the radio spectrum. This phenomenon is explained by a hyperfine interaction that occurs when an electron's spin spontaneously changes. The essence of this quantum mechanical effect is as follows. When a neutral hydrogen atom forms, its electron has an equal probability of having a spin aligned with the proton's spin or in the opposite direction. An atom with parallel spins possesses slightly more energy. Occasionally, a forbidden transition occurs where the electron's spin changes direction. This happens extremely rarely, approximately once every few million years, at which point the atom transitions to a lower energy level, emitting a photon with a wavelength of 21 centimeters. The 21 centimeters line is an invaluable tool for astrophysicists. First, it offers high precision, as nothing else in the universe emits at this specific frequency. Second, this wavelength passes unimpeded through gas and dust clouds. By pointing a radio telescope at a specific location, scientists can determine the amount of hydrogen in that direction based on the intensity of the 21 centimeters signal. In the early 1950s, astronomers Jan Oort, Frank Kerr, and Gart Westerhout, using telescopes in the Netherlands and Australia, first applied this method to study our galaxy. They discovered that gas clouds form spiral arms. Despite the presence of noise, the Milky Way's spiral structure became evident. However, an empty triangle is also observed, caused by the galactic bulge, a dense concentration of stars that obscures objects behind it. Consequently, the far side of the galaxy remains invisible to us, and we can only make assumptions about its appearance based on the symmetry of spiral galaxies. The development of radio astronomy allowed researchers to study the distribution of gas within the galactic disk. However, scientists also wanted to see the stars, hidden behind the dust, that form the spiral arms. The spiral structure of galaxies is defined by massive blue giants, which do not have time to leave their birthplaces. By detecting concentrations of O and B spectral class stars, the location of spiral arms can be determined. However, the ultraviolet radiation from these stars is absorbed by gas and dust clouds. Astronomers found a workaround. They discovered that at birth, massive stars emit strong ultraviolet radiation, ionizing the surrounding hydrogen. This heated and ionized gas forms glowing bubbles that readily emit radio waves. The Orion Nebula is an example of such a region, the only ionized hydrogen region visible to the naked eye. In 1976, French astronomers created a map of the distribution of emission nebulae in our galaxy using a radio telescope. These star-forming regions are located within the spiral arms, where most star formation occurs. The researchers confirmed the Milky Way's spiral structure and identified 4 spiral arms encircling the galaxy. With the advent of space telescopes, the mapping of the Milky Way entered a qualitatively new phase of development. The launch of the Spitzer Space Telescope in 2003 marked a breakthrough, as, unlike its famous predecessor Hubble, it exclusively registered the universe's infrared emissions. Spitzer's decade-long sky survey was an unprecedented step in studying our galaxy. Based on the collected data, a large-scale map of the Milky Way was created, compiled from 800,000 individual images. These images revealed a vast diversity of cosmic objects, but the most valuable result was that infrared radiation, with its ability to penetrate dust clouds, allowed scientists to see over 110 million stars. In 2008, a research group developed specialized software capable of analyzing Spitzer data and determining the density distribution of stars in the galaxy. The logic was simple. Areas with increased star density should correspond to spiral arms. Indeed, it was established that zones of higher density matched the predicted location of the Centaurus arm. However, in the direction of the Sagittarius and Cygnus arms, the telescope did not record a similar increase in density. As for the 4th arm, Perseus, it is located in the outer part of the galaxy, which was not covered by Spitzer's observations. Thus, the data suggested that the Milky Way might not be a 4-armed spiral galaxy, which is quite rare, but rather a more typical galaxy with 2 main arms and several smaller offshoots. Nevertheless, in 2013, Another large-scale study reinstated our galaxy's 4 arms. The uniqueness of this research lay in its focus on finding stars in their earliest stages of formation. Protostars, as they are called, are powerful sources of infrared radiation even at relatively early stages of their evolution. The heat emitted by protostars warms the surrounding dust, which, in turn, begins to glow in the infrared spectrum. Therefore, researchers utilize data from the 2-mass sky survey, as well as information from the older MSX infrared satellite, to identify what are known as massive young stellar objects. Essentially, these are future giant stars in the process of formation, not yet ionizing the surrounding gas. Only in the future will their radiation create luminous regions similar to the famous Orion Nebula. By determining the distances to 1650 such objects, astronomers obtained a new map of the Milky Way, on which 4 prominent spiral arms were once again clearly discernible. It is worth noting that discussions about the number and shape of our galaxy's arms continue to this day. This is because each study employs different methods for determining distances to cosmic objects. While detecting an active star-forming region is relatively straightforward, accurately determining its distance from us is far more challenging. In this regard, immense hope is placed on the Gaia spacecraft, which is currently undertaking a massive census of billions of stars in our galaxy. Its seemingly modest appearance should not be misleading. Gaia has already mapped over 2 billion stars in the Milky Way, and it has done so in 3 dimensions. The secret to Gaia's success lies in its ability to measure star distances with high precision using the parallax method. The essence of this method involves observing a star from 2 different points and measuring the shift in its position relative to more distant background stars. This effect can be observed by alternately closing your eyes while looking at an outstretched finger. Obviously, the greater the distance between the observation points, the more noticeable the shift. For example, one can measure a star's position from 2 opposite points on Earth's surface. Or, one can go even further and use Earth's orbit around the Sun, take one measurement, wait 6 months, and perform a second measurement from the opposite point in Earth's orbit. Then, using simple trigonometric calculations, the distance to the star can be determined quite accurately. Gaia, located at the second Lagrange point and orbiting the Sun along with Earth, measures parallaxes with unprecedented precision, comparable to observing a human hair from a distance of 500 kilometers. Such precision allows for the determination that stars previously thought to be part of a single structure actually belong to entirely different formations. For instance, in 2021, astronomers used Gaia data to analyze the positions of 6,000 young and bright stars, creating the most detailed map of the Milky Way within a region extending 16,000 light-years from the Sun. This represents only a small fraction of the galaxy, approximately 1/6 of its diameter, yet Gaia's accuracy revealed that the so-called local arm, where our solar system resides, is somewhat longer than previously believed. Astronomers hope to expand the scope of their research in the future. However, this comes with certain difficulties, as the parallax method is effective only over limited distances. Stars located on the opposite side of the galaxy may be too distant for their parallax to be accurately measured. Nevertheless, Gaia is not solely a tool for distance determination. The analogy with a forest where trees are stationary is not entirely accurate, as stars, unlike trees, only appear to be motionless. The Gaia spacecraft provides a unique opportunity to study the dynamics of stellar motion, allowing astronomers to track the evolution of the Milky Way. Observations of stellar velocities reveal a general rotation around the galactic center, which is a typical characteristic of spiral galaxies. However, beyond this, our galaxy also contains stars whose trajectories appear anomalous, moving perpendicular to the galactic disk's plane. Within the disk, groups of stars are also observed moving in a direction opposite to the Milky Way's rotation. These features indicate the complex history of our galaxy, which formed as a result of absorbing other galaxies, gradually increasing in size and mass. Today, it is known that the Milky Way's disk stretches for a colossal 100,000 light-years, primarily consisting of empty space, yet containing hundreds of billions of stars and other fascinating forms of ordinary matter. The Solar System, located approximately 25,000 light-years from the galactic center, is situated roughly equidistant from both the center and the edge. Moving around the Milky Way's core at a speed of 220 kilometers per second, the Sun completes a full orbit in about 230 to 250 million years. Thus, since its formation, the Sun has completed over 24 galactic orbits. Within the disk, which is about 1,000 light-years thick, the solar system is positioned near the equator but is tilted at an angle of approximately 60 degrees relative to the galactic plane. It lies between two main spiral arms, Perseus and Centaurus, and appears to be located on the edge of one of the offshoots, known as the Orion Arm or local arm. The size of the local arm, a subject of scientific debate, is estimated at 26,000 light-years. The constellation Orion, after which the local arm is named, is notable for its many bright stars, such as Rigel and Betelgeuse, as well as the famous Orion Nebula. The visibility of these luminous objects is explained by the fact that we are observing the local spiral arm. It's worth noting that the space between the spiral arms is not empty. It contains a significant number of stars, though these are older and less bright than those within the arms. Despite the progress made, our understanding of the galaxy's structure remains incomplete. Existing maps of the Milky Way can be compared to 15th-century geographical atlases of Earth. The main contours are known, but the accuracy of size and distance measurements leaves much to be desired, and some objects are yet to be discovered. New data, particularly from missions like Gaia, are expected to significantly update and refine the Milky Way's map.